They laughed quietly at first, the kind of laughter reserved for moments when professionals think they're being discreet. It happened in conference rooms, during muted video calls, and inside private email threads where no one expected their words to be seen outside trusted circles. When a Philippine-led engineering consortium submitted its structural design for what would become one of the most ambitious coastal megastructures in modern history, several American engineers reacted not with curiosity, but disbelief. The numbers looked unusual, the materials were unfamiliar, and the confidence coming from a country rarely associated with global engineering leadership felt, to them, misplaced. What none of them realized was that they were witnessing the beginning of a story that would permanently challenge how the world defines expertise. The proposal itself was born out of urgency rather than ambition. A sprawling coastal metropolis faced an escalating threat from rising sea levels, intensifying typhoons, and frequent seismic activity. Decades of conventional infrastructure solutions had failed repeatedly, leaving millions vulnerable year after year. International firms offered designs that were massive, rigid, and extremely expensive. They promised strength through resistance, assuming nature could be overpowered with enough concrete and steel. The Philippine team proposed something radically different. Their design emphasized flexibility, adaptation, and movement. Instead of resisting earthquakes, it absorbed them. Instead of blocking storms, it redirected their energy. It was a philosophy shaped by survival. When the proposal reached an international engineering review panel in the United States, reactions were immediate and telling. One senior consultant questioned whether the team had access to advanced modeling software. Another remarked that the calculations looked creative but optimistic. Someone joked that the design relied too much on local experience rather than established Western standards. The laughter that followed was brief but dismissive. No formal rejection was issued, but the message was clear. This was not a design they believed belonged on the global stage. What made the dismissal more ironic was that many of the Philippine engineers had trained in the very institutions now doubting them. They held international certifications, published peer-reviewed research, and had worked on projects across Asia and the Middle East. Yet once their work was associated with a Philippine-led initiative, perception shifted. The assumptions returned quietly but firmly. Capability was measured not by performance, but by origin. Back in Manila, news of the reactions spread quickly within the team. There was frustration, but no surprise. They had encountered this before. Instead of responding publicly, they focused on execution. For them, the project was never about validation. It was about necessity. Every year, storms destroyed homes. Every earthquake exposed weaknesses. Failure was not theoretical, it was personal. Their design was refined relentlessly, stress-tested through simulations and real-world data collected from the region's harshest environments. Sensors were embedded into test foundations. Materials were pushed beyond standard thresholds. Every flaw was corrected before construction ever began. Groundbreaking started quietly. There were no international press releases, no glossy promotional campaigns. Local crews worked alongside engineers who adjusted designs daily based on live data. The foundation system, which critics had mocked as unstable, behaved exactly as predicted. Instead of cracking under pressure, it redistributed stress across modular components designed to move independently without compromising integrity. This wasn't defiance of physics, it was cooperation with it. Meanwhile, skepticism persisted abroad. Online forums speculated about inevitable cost overruns. Blog posts predicted structural failure within the first major storm. Some American engineers framed the project as a case study in overconfidence, waiting for reality to intervene. But month after month, progress continued uninterrupted. The structure rose steadily, efficient in form, purposeful in design. It didn't look like a monument, it looked like something built to endure. What truly set the project apart was its intelligence. Every component served multiple purposes. Structural supports doubled as energy conduits. Flood channels functioned as pressure release systems. Materials sourced locally outperformed imported alternatives, not despite their origin, but because they were designed for the environment they inhabited. This efficiency unsettled outside observers. How could something so unconventional work so well? Quietly, a few American firms requested access to preliminary performance data, framing their interest as academic. What they found challenged everything they thought they knew. Stress margins exceeded international safety standards. Cost efficiency projections were dramatically lower than comparable Western projects. Maintenance requirements were minimal. The numbers were not exaggerated, they were simply different. And that difference was becoming impossible to ignore. The project moved forward, unnoticed by mainstream media, but increasingly impossible for the engineering world to dismiss. The Philippine team remained focused, knowing that the true test had not yet arrived. Nature, they understood, would eventually demand proof, and when it did, there would be no room left for laughter. The first real test came sooner than anyone expected. Weather systems in the Pacific intensified rapidly, merging into a typhoon strong enough to trigger emergency alerts across the region. Local residents prepared for the familiar cycle of evacuation and loss, while international observers watched closely. In engineering forums, the tone shifted from mockery to anticipation. This, many believed, was where theory would collapse under reality. The Philippine team monitored the data calmly. They had designed for this moment, not hoping to survive it, but expecting it. As the storm made landfall, wind speeds climbed beyond initial forecasts. Waves surged higher than historical averages, slamming into the coastline with relentless force. Traditional structures nearby shut down as a precaution, but within the megastructure, systems remained operational. Sensors embedded throughout the framework transmitted live data, showing controlled stress distribution exactly as modeled. Instead of rigid resistance, the structure flexed subtly, absorbing and redirecting energy through its adaptive joints. What looked fragile to critics was proving to be remarkably resilient. When the typhoon finally moved inland and weakened, assessment teams moved in. Engineers walked the site methodically, checking joints, foundations, and load-bearing components. There were no critical failures, minor surface wear exactly within expected parameters. Data logs confirmed what the visuals suggested. The design had not been lucky, it had performed precisely as intended. Within hours, footage and sensor readouts began circulating online, first within engineering circles, then beyond them. The reaction was immediate and dramatic. The same forums that once dismissed the project exploded with analysis. American engineers replayed clips frame by frame, comparing stress data against their own models. Some questioned the authenticity, others demanded independent verification. That verification came quickly. An international monitoring agency released its findings, confirming the structure's performance and validating the Philippine team's methodology. The silence that followed was louder than the laughter had ever been. Requests for information poured in. Engineering departments asked for technical papers. Firms requested briefings. Conference organizers sent invitations that had been unthinkable months earlier. The Philippine engineers responded carefully, prioritizing transparency over triumph. They released data, explained their philosophy, and emphasized that the design was not a miracle, but a response to specific environmental realities. Still, the shift in perception was unmistakable. What had once been treated as an experiment was now being studied as a breakthrough. In the United States, internal conversations grew uncomfortable. Some engineers revisited their earlier comments with embarrassment. Others defended their skepticism as due diligence. But privately, many acknowledged a deeper issue. They had equated unfamiliarity with inferiority. They had assumed innovation followed a predictable geographic path. The storm had shattered that assumption as thoroughly as it had tested the structure. As weeks passed, the megastructure continued to operate flawlessly. Smaller storms followed, each reinforcing the same conclusion. Maintenance costs remained low. Adaptive systems adjusted automatically. Local governments reported increased economic stability in surrounding areas. The project was no longer just a defensive barrier. It had become a functional hub, supporting transportation, commerce, and energy generation simultaneously. Its success rippled outward, challenging long-held beliefs about who could lead at the highest levels of engineering. For the Philippine team, attention brought mixed emotions, pride certainly, but also a quiet sense of inevitability. They had never doubted the design. They had doubted whether the world would listen. Now, listening was unavoidable. Invitations arrived from institutions that had once overlooked them. This time, there were no jokes, only questions, notes, and a growing realization that the future of resilient infrastructure might look very different than expected. The laughter was gone. In its place was something far more powerful, reckoning. And as the world began to reassess what it thought it knew, the story of this project was only just beginning. As international attention intensified, the Philippine team found themselves navigating a world that suddenly wanted access to everything they had quietly developed over years. Requests arrived daily: technical briefings, simulation walkthroughs, site visits. Universities asked for guest lectures. Governments asked for feasibility studies. Even firms that had once dismissed the project now sought collaboration. The engineers responded deliberately, refusing to rush explanations or simplify their work into sound bites. They understood that the value of the project lay not only in what had been built, but in how it had been conceived. At the center of their approach was a principle many had overlooked. Environments are not obstacles to defeat, but systems to understand. The team explained how their designs were informed by historical data, indigenous construction practices, and decades of observing how structures failed under stress. Instead of designing for ideal conditions, they designed for worst-case scenarios, assuming uncertainty as the default rather than the exception. This mindset, shaped by living in a disaster-prone region, had given them an edge that no imported blueprint could replicate. American engineering institutions began dissecting the project in detail. Case studies replaced criticism. What stood out most was not a single innovation, but the integration of many small decisions that worked together seamlessly. Flexible joints, adaptive load paths, and modular components were not revolutionary on their own. What was revolutionary was how they had been combined, optimized, and implemented at scale. It forced a difficult question within the profession. How many innovations had been ignored simply because they didn't come from familiar places? Behind the scenes, internal reviews took place at major firms. Early skepticism was re-examined. Emails once written casually were reread with discomfort. Some engineers recognized that their objections had been less about engineering rigor and more about instinctive doubt rooted in reputation. The realization was not easy. Engineering prided itself on objectivity, yet here was proof that bias could exist even in the most data-driven fields. Meanwhile, the megastructure continued to evolve. Its adaptive systems learned from every environmental event, fine-tuning responses and improving efficiency. Engineers treated it as a living laboratory, collecting data that refined future designs. Each update strengthened the case for resilience-first infrastructure. Other countries facing similar threats took notice. Delegations from island nations, flood-prone deltas, and seismic zones visited the site, eager to learn from a solution that had proven itself under real conditions.
In the United States, some of the earliest critics became unexpected allies. They spoke candidly about being wrong, about how comfort with established systems had narrowed their thinking. These admissions were not public apologies, but they were sincere. They marked the beginning of professional humility, a recognition that innovation does not announce itself in familiar accents or formats. The project's influence extended beyond engineering. Policymakers referenced it when discussing climate adaptation. Economists noted its cost efficiency. Urban planners studied its integration of infrastructure and community needs. What had started as a single structure was now reshaping how societies thought about building in an uncertain future.
Yet, for the Philippine team, the work remained grounded. Recognition did not change their priorities. They continued refining designs, mentoring young engineers, and documenting lessons learned. They understood that success was fragile if not shared. Knowledge, they believed, only mattered if it traveled. The world had begun to listen, but the story was far from over. The real test, they knew, would come not from one project, but from whether the lessons learned would be applied elsewhere. And as new challenges loomed on the horizon, the quiet confidence that once drew laughter was now drawing something else entirely: respect. As the project's reputation grew, its influence began to reach places far beyond the original coastline. Governments facing similar environmental threats started to ask uncomfortable questions about their own infrastructure strategies. Why were they still investing in rigid, over-engineered solutions that failed repeatedly under extreme conditions? Why had resilience been treated as an afterthought rather than a foundation? In closed-door meetings, policymakers pointed to the Philippine megastructure as evidence that a different path was not only possible, but necessary. International funding institutions took notice as well. Risk assessments that once penalized projects in developing regions were quietly revised. The data coming from the structure was impossible to ignore. It showed consistent performance under stress, predictable maintenance costs, and long-term sustainability. What had once been considered a risky experiment was now being cited as a benchmark. This shift unlocked financing for similar projects across vulnerable regions, many of which had previously been denied support.
The engineering world began to change in subtle but meaningful ways. Conferences that once centered almost exclusively on Western case studies expanded their scope. Panels included voices from regions historically treated as peripheral. The Philippine team was frequently invited, not as a novelty, but as leaders in resilience-based design. Their presentations focused less on triumph and more on process, emphasizing that innovation thrives when engineers are allowed to learn from failure rather than fear it. Back home, the impact was deeply felt. The success of the megastructure transformed how engineering was perceived nationally. Young people who had once dismissed the profession as undervalued began to see it as a path to global relevance. Universities updated curricula to include adaptive design principles drawn directly from the project. Local governments invested more heavily in research and development, recognizing that homegrown expertise could compete on the global stage.
The megastructure itself continued to operate quietly, almost anonymously, doing exactly what it was designed to do. Each storm reinforced its credibility. Each year without major repairs strengthened the argument behind its philosophy. Engineers monitored its performance continuously, refining models and sharing insights with collaborators worldwide. The structure was no longer just protecting a city, it was informing a global shift in how infrastructure was conceived. American engineering firms, now openly engaged, began forming joint ventures with the Philippine team. The dynamic was noticeably different from the early days. Conversations were grounded in mutual respect. Assumptions were challenged openly. Solutions were co-developed rather than imposed. In many ways, the collaboration produced better outcomes than either side could have achieved alone. It was proof that humility could be a powerful engineering tool. Privately, some of the earliest skeptics reflected on how close the world had come to missing this breakthrough entirely. Had the project failed early due to lack of support, its ideas might have been dismissed permanently. The realization was sobering. It highlighted how many innovations may have been lost in the past, not because they were flawed, but because they came from voices that were not heard. The cultural impact extended beyond engineering. The story of the megastructure became a reference point in discussions about global inequality, representation, and trust in expertise. It was cited in classrooms, documentaries, and policy debates as an example of how progress is slowed when credibility is tied to geography instead of evidence. The narrative shifted from surprise to accountability. Despite the growing attention, the Philippine engineers remained cautious. They resisted being framed as symbols of national superiority. Their message was consistent. The success of the project was not about proving others wrong, but about proving that diverse perspectives make systems stronger. They emphasized that climate challenges did not recognize borders, and solutions could not afford to be limited by them either. As new projects inspired by the megastructure broke ground around the world, a quiet transformation was underway. The industry was beginning to value adaptability over dominance, listening over lecturing. The laughter that once followed unfamiliar ideas had been replaced by curiosity, and with that shift, the future of global engineering looked fundamentally different. Over time, the story of the megastructure settled into something more enduring than headlines or professional debates. It became part of the everyday reality of the city it protected. Families rebuilt their lives with confidence. Businesses invested without fear of the next storm. Children grew up watching severe weather pass without the panic their parents once knew. For the people living there, the structure was not a symbol of global recognition. It was proof that thoughtful design could quietly change the course of ordinary lives. In international circles, however, its legacy continued to grow. Engineering standards committees began revising guidelines, incorporating adaptive and resilience-first principles drawn directly from the project's data. What had once been dismissed as unconventional was now written into official frameworks. The shift was subtle but profound. It signaled an industry learning to value evidence over assumption, performance over reputation. The Philippine team watched this transformation with cautious optimism, knowing how easily progress could reverse if humility was lost. Some of the American engineers who had initially mocked the design eventually spoke about the experience in lectures and interviews. They described it as a turning point in their careers, a moment when they realized expertise does not belong to a single culture or institution. Being wrong, they admitted, had made them better engineers. It forced them to listen more closely, to question instincts they once trusted without examination. Those reflections, though quiet, carried weight among younger professionals. The megastructure itself remained unchanged in its purpose. It adapted, learned, and endured. Each year added to its record of reliability. Each environmental challenge reinforced the same lesson. Systems designed with respect for uncertainty outperform those built on rigid confidence. This lesson echoed far beyond engineering, influencing how organizations approached risk, planning, and collaboration in an increasingly unstable world. For the Philippine engineers, the journey never felt like a victory lap. It felt like responsibility. They continued mentoring students, sharing research openly, and advocating for inclusive collaboration. They reminded audiences that the most dangerous failures often begin with dismissal. That laughter, when it replaces curiosity, can delay solutions the world desperately needs. Looking back, the early mockery seemed almost small compared to what followed, not because it was forgotten, but because it was outweighed by impact. The structure stood as a quiet correction to a flawed assumption, that innovation must come from familiar places to be trusted. It proved that brilliance, when grounded in experience and tested by reality, speaks for itself. And now, as this story comes to a close, it's worth asking what lessons we choose to carry forward. If this journey changed how you see innovation, resilience, or where expertise can come from, let us know. If you found value in this story, make sure to like the video, subscribe to the channel, and share it with friends who might need to hear it. And most importantly, comment below with your perspective or the key lesson you're taking away, because conversations like these are how real change begins.